In this video, I want to go over how to compute the flux of a particular function. It's somewhat difficult. It's in the review section of the final chapter. So we want to compute the flux of this function f, which has a scalar multiplier in the denominator of x squared plus y squared plus z squared raised to the 3/2 powers. And the numerator is the vector x, y, and z. So we want to find the flux of f across this ellipsoid, which consists of points x, y, and z, such that 4x squared plus 9y squared plus 6z squared equals 36. Okay, so just as a reminder, this is the flux of f across S, and by direct computation, or rather you could say by definition, this integral is equal to f dot n ds, right? So in your book, they use a boldface S. I use the $sign. That's my style. So, well, what is this in? This is a normal vector. Normal to what? Well, normal to the surface S. So if you think back to your early days of this course, when you have a plane, say ax plus by plus cz equals d, the normal vector to that plane is the vector a, b, and c. But when you have a curved surface, just as the curve is changing, so does the vector on the surface. So we need to find the normal vector on an ellipsoid. Now, if you think of a sphere, if you have a perfectly round sphere centered at the origin, the normal vector at every point on the sphere is just going to be x, y, and z, right? Okay, so what about the ellipsoid? That's a little more complicated. It's not immediately obvious to me what it is, but in your take-home exam, in your assignment, you were asked to compute the normal, or rather, compute the tangent plane to a surface when you don't know the surface, but you know two curves along the surface. Once you have those two curves, you can find the tangent plane. And if you have a tangent plane, you have a normal. I can't tell you how to do that because I'd be giving away the exam, but do that and you could apply it to this. So in this case, we actually know exactly what the surface is. So how much more information we have in this case than we do on the exam. Then all you have to do to find n is take, you have this this surface, right? And all you got to do is compute these two curves, right? And then where they intersect, you find the tangent plane to it using the techniques from the exam. And once you have the plane, you have the normal vector to the plane. And because it's normal to the plane, it is also normal to the surface. That is a lot of work, and we don't like to waste time. So I will leave that as a fun project if you would like to do, but let's actually solve this problem. So we have a very powerful result known as the Divergence Theorem. And it says you don't have to compute that. That's a lot of work. So instead, we're going to transform this into, so this is the Divergence Theorem. This is going to allow us to convert it into a triple integral on the entire object, not just its surface, so the entire object. Then you take the divergence of f and it with respect to volume. Okay, so great. Now, it seems like things are more complicated, and they are for the integral. But it's going to turn out that the divergence of this is very, very nice. So what is E? Well, E is the entire ellipsoid, okay? This entire thing, not just its surface, but all the values, not just that satisfy this, but all the values inside of that. So it's actually now going to be E is equal to all the values less than or equal to that, because they're going to be inside of it, so less than or equal. So for example, 0, 0, 0 is in this ellipsoid. Well, let's go ahead and compute the divergence. So the divergence of F, this is going to be the partial of F with respect to X plus the partial of F with respect to Y plus the partial of F with respect to Z. Now, as you can see, the function is rather symmetric, because when I compute the partial with respect to X, when I look at the denominator, I have these terms. When I compute the partial with respect to Y, I look at the denominator, I still have those terms. But when I look at the numerator, I'm only looking at the particular, sorry, this is not correct. All right, this should be P, Q, and R, right? Where F is equal to P, Q, and R. When I do this, when I look at P, and I take it with respect to X, there's an X there. When I look at Q, and I take it with respect to Y, there's a Y there. You also cannot forget about the denominator, but the point is that if I compute this for X, then I also get it for Y and for Z by symmetry. Okay, so we're just going to compute del P with respect to X. Okay, so del P with respect to X. Okay, so let's do this. So the partial with respect to X of P, well, P is what? It's this right here. So it's X times, well, when you multiply a scalar, you do it to each part. So it's already in there. So this is X times X squared plus Y squared plus Z squared raised to the negative 3/2 power. So I'm going to compute the derivative of this holding X constant. So hold X constant. Take the derivative of the outside, it goes to the front. So negative 3/2, right? Inside X squared plus Y squared plus Z squared. Subtract 1 from here, so that's negative 5 over 2. And then multiply the inside, and I get 2x. Okay? Now, sorry, not multiply. Multiply by the derivative of the inside with respect to x, which is 2x. Now I want to take the derivative of the first part, that's x, so we should just get 1. So this is x squared plus y squared plus z squared to the negative 3/2 power. We left the second part constant. Okay, so let's simplify. Well, these 2's are going to cancel, and I don't like that negative, so I'm going to put it to the bottom, and when I put it to the bottom, I get this, right, to the 5/2 power. Okay, so x times x is x squared, and then there's this negative 3, so negative 3. Now, I have this extra bit right here. So in order to get a common denominator, I need to multiply by this, right? Okay, so I'm just multiplying it by 1 in a clever way, and when I combine them, the bottom is going to be that, and then the top is just x squared plus y squared plus z squared raised to the 2 over 2, which is just raised to the first power. So I can rewrite this as x squared plus y squared plus z squared. And let us simplify this. So I get, well, that's 3 and 1, so that's negative 2x squared plus y squared plus z squared, all divided by x squared plus y squared plus z squared raised to the 5/2 power. Okay, so to summarize, this is going to be x squared plus y squared plus z squared raised to the 5/2 power, y squared plus z squared. Okay, and then negative 2x squared. Okay, so I wrote it in a different color for a good reason, because we have that symmetry, right? So obviously, when I compute the other coordinates, right, I'm going to get partial with respect to q. I replace, every time I see an x, I replace it with a y. Every time I see a blue x, I replace it with a blue y. So in this case, I should get x squared z squared over x squared plus y squared plus z squared negative 5/2, and then minus 2y squared plus z squared. Okay, and then for del r by del z, what do I get here? Again, we're going to do the same trick. So minus 2z squared, and then I'm going to divide that by x squared plus y squared plus z squared raised to the 3/2 power. And what is the divergence? Well, the divergence of f is going to equal partial of p with x, partial of q by y, and partial of r by z. Well, let's look at x. So negative 2x squared plus x squared plus x squared. Okay, so that's 0 in x squared. What about y? So plus 1 minus 2 plus 1. Okay, that's also 0. What about z? 1 plus 1 minus 2. Okay, so effectively you get 0. So the divergence of f is 0, and although the ellipsoid is very complicated, it doesn't matter. So the takeaway from here is that it's kind of a trick question, because you could have computed it. You could have worked really hard to get that that tangent plane and the normal vector to this ellipsoid, and you could do it. But ultimately, what we see is that the divergence of this function, no matter what the object is, it's going to equal 0. So the takeaway here is that it really does not matter what kind of surface that is. S could be literally anything as long as it is a surface, right? Then when we apply divergence, we pick up, so it's got to be a surface of a three-dimensional object, right? The boundary of a three-dimensional object. When we compute E, right, whatever that is, the divergence of F across that is always going to be 0, and so we conclude that the integral is equal to 0. Okay, have a good day.